So last time, we started talking about supersymmetrical mechanics, and we introduced Q, charge Q, physical supercharge, which map the bosonic Hilbert space to the Fermat Hilbert space. And essentially, the supercharge can be understood as the square root of Hamiltonian. So it's like so the way I explained is that the triangle equation, Dirac equation is the square root of triangle equation. So likewise, supersymmetric charge is some square root of a time translation Hamiltonian. So then, and then we look at the computational relation between Hamiltonian supercharge 0. Dagger 0. And then since only the Q is sensitive to V, Q diagram has B, so therefore this becomes V. Oh, sorry. So let's assume the V is the bosonic eigenstates of Hamiltonian, and then we consider some superquantum of the bosonic eigenstates. Then Hamilton, the energy of this Fermat partner, superpartner is indeed Q plus Q. So that we just look at the sorry, it's B. Sorry, B Q Q B. So then this is indeed sorry. What am I doing here? Yeah, QQ dagger acts on B will give you EB, and which commute with EB is just number. You commute with Q, so you get that this is equal to EB F. If EB is non-zero. So that's what we have seen. Therefore, and vice versa. So given a Fermat eigenstate, for instance, B, F, then the superquantum can be defined as like this way, and then HB can be HF. Therefore, if the states are related by supercharge, QQ dagger F with non-zero eigenvalue, then they form the super partner, one-to-one correspondence. So that in the energy spectrum, you always have a Fermat boson. Fermat boson. Okay. Where the zero stays here, you have a pair always. So this will fail once you have the once you look at the ground state, which is equal to 0, so that the so you can just take a look at the H, which means that the HB equal to 0. This will give you the condition B Q Q B. I think is it the Q? Yeah, Q dagger is equal to 0. So therefore Q dagger QB is indeed 0. Okay. So this means okay, so the same thing happened in the Fermat case. So when you look at the Fermat ground states, then so this means finalized Fermat. So as I mentioned, so the supercharge is the square root of a time translation. So therefore, exponential. So this will give you time translation. In the quantum mechanics. On the other hand, this will generate some fermionic translation. So it's a square root, and then so since this will annihilate, so the ground states will be annihilated by a supercharge Q. So the bosonic states of ground states is equal to the same. The same thing happens for Fermat ground states. So it acts like a 0. So therefore, it's just acts as identity. Okay. So therefore, so these are called invariant and supersymmetric transformation. Okay. Therefore, the ground state is sometimes called a supersymmetric state. So B F with equal to 0 are called supersymmetric ground state, supersymmetric states. Because it's invariant under supersymmetric transformation. Okay. Okay. So on the other hand, okay. So then so that what's going to happen is that maybe instead of writing here, I can write on a bigger space. For excited states, you have a pair between supersymmetric partner or whatever, E and F, okay, E and F. But for ground state, you don't have such a pairing. So for excited states, you have a pairing. You have a bunch of bosons, and you can have bunch of fermions. They don't need to be supersymmetric partners. Okay? So the number of boson fermions are not balanced at the ground state. So when in 1982, so when introduced the following quantity, traces taking over here space, boson and fermion, minus 1 to the f is the minus 1 to the f acts on bosonic states. So this is fermionic operator, so it counts fermion by 1. So this is just plus sign, minus 1 to the f, you get the minus sign, okay? So this is how you get, okay? The how you minus 1 to the f acts on, and then the trace means you just sandwich by states. So sum over all states. So this means indeed equal to minus 1 to the f sum over whatever boson or fermion minus 1 to the f boson or fermion, and the B or F is sitting here with this. So you just count by sign. Okay? If it is boson, you get the plus sign. You get the fermion, you get the minus sign. That's it. So on the excited states, you have each pair you get the cancellation, plus sign and minus sign for excited states. Okay. Therefore, this will become number of bosonic ground state minus number of fermionic okay. So it just gives the number of the difference between bosonic and the fermionic ground states. In this example, 2 minus 4, so you get minus 2. So in this example, trace of minus 1 to the f is equal to minus 2 in this example. Okay. So even though there are the infinite many states, you only need to look at the ground states. Okay? It's very similar situation what the Fredholm operator is defined. So okay. So the index theorem, when we introduce index of some operator, the elliptic operator, which is the dimension of kernel of D minus dimension of co-kernel of D. And as I mentioned, sorry, my voice is. So the space, I forgot that I call it E and F, as far as I remember. And then D maps like this way, and the kernel is like this way. Even though it's an infinite, sorry, I think a section of that. So this is infinite dimensional. So what's relevant is finite dimensional guy. So if it is the elliptic operator, this becomes finite dimensional, and this becomes finite dimensional. Okay? Even though the rest of the part is infinite dimensional. Okay? So we just look at only the dimension of the finite dimensional piece. This is exactly what's happening in pseudosymmetric quantum mechanics. Even though bosonic state and fermionic state, there are infinite many bosonic states and fermionic states. Nonetheless, you can only look at the ground state, which is most likely the finite numbers. Okay? So it's a very similar situation we would have. And moreover, so this can be understood as the dimension of kernel of Q and minus dimension of kernel of Q dagger. So it's very similar to if you apply, so this D as the drum differential, and it's Hodge-Dell, and this can be written as dimension of kernel of yeah, I think okay. D plus delta restricted to even, and then the same thing. Dimension of kernel of D plus delta restricted to delta. Okay. That's what we have seen, and it's very similar to what I have written over there for pseudosymmetric quantum mechanics. Okay. And now, so let's look at the how it acts. So remember, Q and Q dagger. So I already seems like I mean the last time I mentioned the Q. So Q and Q dagger is equal to square root to I already really saw dx plus w prime, whereas this is minus. Okay. So therefore, the Q analysis of the states, really functional language, it can be written like this, okay? in terms of differential equation. And then we just want to look at the solution of this one, which can be easily solved. I mean, as you know, you can easily solve phi of x is exponential of plus minus w of x. Okay? That's the solution. Oh, sorry, I think minus plus. These are solution for this differential equation. It's just an ordinary first order linear equation. Okay. And we also impose 5x 0 as x goes to infinity. Okay. So therefore, and then if we suppose, if we assume this W has a polynomial growth, okay, so at it goes to infinity, it behaves like lambda x to n. Let's consider this situation when for at x goes to as x goes to infinity. Okay. So if n is even, so if n is even, there is so there exists the bosonic, or I mean, if it is x to the even, so everything is how to say, goes to polynomially positive, right? So therefore, if you pick minus sign, it decays to 0. Okay? So therefore, there exists zero energy solution. There exists a solution. One solution to this guy, to this guy with this boundary condition, this is boundary condition. On the other hand, if n is odd, so it changes sign. So if it is, if positive infinity goes to how to say positive, then if you go to negative infinity, it goes to negative. So there is no solution which satisfies this boundary condition. You understand what I mean? So for even, you have for even. Okay, depends on lambda. So for if it is even, so whatever, like this way, if lambda is positive and the n is even, so then solution is exponential of minus w of x. And then if lambda is negative and the negative even, it becomes like this. Okay? So therefore, solution is exponential plus w of x. Okay? Plus w. On the other hand, on odd, whatever lambda takes, essentially it takes like this way. Okay? Therefore, both of the solution does not obey this normalization condition. Can you see that? So if you pick minus sign, W has to be positive infinity. But here, if you go to negative infinity of x, you have a negative sign for W. So what I meant is this is Wx. W and x and W and x. Okay? So there are, so if n is no solution. Okay? So therefore, this will give you a trace of -1 to the f is either plus minus 1, depending on the value of lambda. On the other hand, here trace of -1 to the f is equal to z. There is no bosonic parameter ground source. Okay? Do you understand what I mean? And this is exactly what we have seen in the first lecture. Do you remember? The first lecture, I just give you the. I don't print out that part, so let me look at my. Yeah. So let me look at my note on computer. Okay, the computer, and then so we just last time we look at like this. Oh, what was that? Yeah. So what we have seen is that so we just look at the supersymmetric quantum mechanics, and the partition function is given by dx, and then some are probably known like ds dx, and then dx dt. Sorry, this is t maybe. And then sorry. There are lots of mistakes. Sorry. Don't copy and paste from. Sorry. dx, ds, dx, and then minus 1/2 s squared x. So we just consider partition function like of this kind, and then we introduce some parameter which t. I introduced parameter t in the beginning of the lectures. I already forgot and put t here by just scaling s. And so therefore this is t squared indeed. Okay? T squared indeed. And when you take t goes to infinity, so everything localized. So everything localized, the configuration s is equal to 0. So what we saw is that everything's x, sx is equal to 0, such that the dx sine of ds over dx sum over sine of dx. Okay? That's what we have seen at the point xi. Okay? So that's what we have seen, and this is equal to sum over xi and plus minus 1. And if you look at the let's see, even function to the 4 point. Okay, there's a 4 point here, and everything, the slope is minus 1 plus 1 and minus 1 plus 1. Okay, this is equal to 0. So this will give you z is equal to 0, whereas this is s and x. Okay. If you have the odd function, you have plus 1 and minus 1 and plus 1. Okay. And this is equal to z is equal to plus 1. And then, so later I just introduced s is equal to w prime of x. Okay? Later, so it's the first derivative of some so-called superpotential. So therefore, if you compare the right black ball and left black ball, if you take even function and take derivative, one derivative, it becomes odd function. Okay? Therefore, this will reduce this to this case. Okay? And then plus 1. And then if you take derivative of odd function with even function, this will reduce this to uppercase. So therefore, they are consistent. Okay? And then from here, we look at this is very similar to Poincare-Hopf theorem. Okay? Poincare-Hopf theorem. Okay? Poincare-Hopf theorem. Do you remember Poincare-Hopf theorem? Can you write a statement of the Ponger-Hopf theorem? Can anybody write statement of Ponger-Hopf theorem? I really wish some of you guys can write down the statement of Ponger-Hopf theorem. One of the main theorems of this lecture. And also you use it to solve some of homo. If G is compact Lie group, order characters is what? If compact Lie group, if G is the compact Lie group, order characters of compact Lie group is what? Zero. Why? Huh? What did you say? Just speak up. It's okay. Even if you make a mistake, why it becomes zero? You guys solve homework, right? Why it becomes zero? So if you take the G acts on G as a left action. So if you pick some left action, okay, and G can take for instance exponential sum vector field times t. Okay, when t goes to zero, it's just identity map. Okay, and t is non-trivial, it's just left translation. That will give flow of the vector field x. Okay, there is no fixed point. There is no zero of the vector field. And Ponger-Hopf theorem tells us that the order characteristic of M is sum of a vector field, zero of vector field, and then index of point P of x. Okay. P is a zero of the vector field, okay? And x is a vector field in compact manifold. Compact cross manifold, oriented manifold. Okay. Okay. So that's the Ponger-Hopf theorem, and it's very similar to what we have seen in supersymmetric quantum mechanics. Okay. So that's the connection to the first lecture, and then now I can talk about the index theorem a bit more, but yeah. Yeah, so that I should make a remark. Okay, so then, so even if Hamiltonian is supersymmetric, so this, if the superpotential is even function, there is supersymmetric states, at least one, either Fermat both. Whereas if it is odd, okay, if it is odd, if it is odd, there is no supersymmetry. The index is zero. So there is no supersymmetric space. So therefore, even though Hamiltonian is supersymmetric, there is no supersymmetric states. So therefore, it's called a supersymmetry. Supersymmetry is spontaneous broken. Okay, spontaneous broken. So that's the upshot of the lectures. So I just tried to connect the first lecture to the end of lecture. So 2 lectures are left, including today. So less of time, I will talk about a bit more advanced topic. Yes.
So the ground state y is more than 1 for the ground state equation should follow the closely principle.
I'm sorry, could you repeat again?
I mean,
What is
in
it?
your picture, you have more than one finite ground state.
So I have I put 4.
Yeah, why is not say the Pauli inclusive principle?
Pauli, what is it called? Pauli exclusive principle even.
Yeah.
So they're not the same states. Sorry. Maybe I should put the 1, 2, 3, 4. They're not the same states. Sorry. Maybe 1. I think, or maybe I should add AB.
So they are zeros.
Yeah. But they're not the same states. There is some other quantum numbers that distinguish. Okay. But this is very generic phenomena in supersymmetric field theory. Whatever, if you go to, it's quantum mechanics, so it's very simple. But if you consider supersymmetric field theory, I mean quantum field theory plus supersymmetry, even states obey this phenomenon. And the trace of -1 to the f, this quantity plays very important role in supersymmetry. Even I always compute this one. I always, in my research, to compute trace of -1 to the f is one of the main tasks in my research. And also he's doing such a computation. Anyway, always, I mean, if you try to understand supersymmetric field theory, you always encounter this counting of Hilbert space up to -1 to the f. Every time it appears. Yeah. So most of the time I try to compute or give mathematical meaning of this object. Given a supersymmetric field theory, compute this quantity is one of the main tasks of the under research in supersymmetric field theory. Okay. And if you're interested in, you can just take a look at 1982 paper by Wesson. The 2 paper. One is, let me check now in that case. One is the supersymmetry and Morse theory. This paper is actually, when I was an undergrad student, I told you I studied GR because I'm interested in the geometry and physics. But this paper brings me to the territory of supersymmetry and so on. Exact result in supersymmetry. It's very impressive. I highly recommend you to read. You can just. It's not that long paper. It's a wonderful paper, and another paper is it's a really more physical. Let's see. Oh yeah. Another paper is dynamical braking. This is a more physical paper. Dynamical braking. Braking. Both of supersymmetry. Both are 1982, and then just try to understand what the trace of -1 to the f means in supersymmetry. This one is rather long, but more physical. And then the upper one is the concise, and then it gives a relation to topology and the supersymmetry. Okay, so that's the story, and then so this is 1982. From here, so this is a toy model, it's a supersymmetric quantum mechanics. Roughly, I just sketched the essence of this paper actually, indeed, in my lecture. Even though I didn't introduce Morse theory, this is 1982, and in 1988, there's a remarkable paper by Wood, 3 papers, which is the main motivation in my work. And the TQFT, topological, he introduced 3 types of topological quantum field theory. This is 4 dimension. Another is the 3 dimension, this is 4 dimension. Another is the QFT and Jones polynomial. This is 3-dimensional. And then 2D, what is the title? Topological sigma model? Let me check now. I should have known, sorry. When I was a student, I keep reading these 3 papers. That was the one that was my task in, how to say, when I was a student. Or graduate student, when I was graduate student. Witten has written too many papers, so I cannot identify it. Where was it? Oh yeah, I found it. Topological sigma model is correct. So topological sigma model. So these 3 are the paper. And today I'm going to talk about, so these 3 supersymmetric quantum mechanics, but their generalization quantum field theory. It's nowadays called topological quantum field theory, and I will talk about this guy today. Okay, what is the Chern-Simons? So today I'm going to talk about Chern-Simons theory. I don't know how far I will get. And the next lecture I will talk about modular space. And even today I will talk about a bit about the modular space. So let's first talk about Flat connection. So Flat connection is the Flat connection. So let's consider the principal G bundle. So this principal G bundle. Okay, and A is a connection. Is a connection. Okay, and then so you can just consider the curvature. F is EA plus A wedge A, and this is the curvature. If F equals 0, A is called flat connection. Of course, often P principal G bundle with the flat connection A. F is equal to 0, so this pair is called flat G bundle. So as I mentioned, so if given a principal G bundle, so given a principal G bundle, there's a P and M here. So this is a projection. And at each point, you have the fiber, which is G itself. Okay? G itself. And then what the connection does is that they just define the flux direction. What connection does is define the flux direction in a principal G bundle. And more precisely, so we just it's, by the way, so these papers definitely they're available online. So whatever, even if you cannot understand, just open and try to skim over. And if possible, try to understand. It's quantum mechanics. So it's it'll define the oops. So it defines horizontal direction. The connection defines horizontal direction. These are horizontal direction. So the connection will define, A will define horizontal direction in such way as follows. So HU is equal to x, which is the tangent vector at point U, and x is equal to 0. So this is one form, A is a one form, and x is the tangent vector at point U. Therefore, you can just have a parent. And if it is 0, it becomes horizontal vector. Okay? And if you consider the collection of horizontal vector, so this is called distribution. It's called distribution. So namely, so at point U, okay, at point U, you can just define the horizontal direction, x. Then x is a tangent vector at point U here. And if you take contract with an x, you get 0. That's a horizontal direction. So so if you take at each point the collection, so this is H, like how to say, this subset of H. Subset of H. Okay. And I cannot draw, it's amazing, it's only, I can just write down the manifold is one-dimensional and the fiber is one-dimensional. That's the best I can do. But of course, given the horizontal vector, so horizontal vector field, if okay, so if commutator is also a horizontal vector field for given any x and y, horizontal vector field, then this distribution H is called complete integral. So another way, so to see that, for instance, if you take you can take contraction, so x and y, they as the horizontal vector field. So then dA plus which A, and take the contraction with two vector field, and we know that it's horizontal vector field. A contract with x is 0. Okay, A contract with y is 0. Okay, therefore what we have is VA with the x and y. Okay. And then you just apply the usual differential relation. You have 1/2 x ay, okay, and then y ay. Oh, sorry, x minus a y is equal to of a x and y. So therefore, if if x and y or this h is completely integrable, then f is equal to 0. If only, sorry. So this is it's the same, if and only. If f is 0, it's also completely integrable. If completely integrable for any x and y, f is also 0. So, okay. So therefore, another way to see this distribution is as follows. So let's see. So if f is so therefore it's hard to describe. So given a point, so the principal G bundle and point look at here, point U, and here look at the horizontal direction. It's very difficult to describe, but just zoom into this around this part, and you have horizontal direction x and y. So the horizontal direction tangent. Horizontal direction with respect to this connection. So this x, y is also inside HU, means that you can just integrate out. So this direction, it becomes submanifold. So it's okay. I shouldn't say. I mean, one can have submanifolds that contain x and u. So that will create submanifold n inside n. Inside P. Sorry, inside P. Submanifold. Such that the tangent of u point n is indeed I can be identified with the distribution of point. So now we consider the following thing. Unfortunately, I cannot draw the. Okay, let's do the following. So by Stokes theorem, so there is a manifold M. Okay, and at the point, each point you have 5 G. At each point 5 G, and then you just consider some loop. Okay, loop. and you start with u, point u, okay? And there's a parallel transport one can do. So you can do the parallel transport. So the red line is horizontal, always horizontal. So the given a connection, so there's a P here, and map to M, and the connection define the horizontal direction. There's the connection A here that define horizontal direction. And given a start point U that map to point P by projection, and do the parallel transform along the base, along the cycle at the base manifold, along, okay? And if there's no, if this loop is contractible, okay? If this loop is contractible, and f is equal, if the flat connection, if it is f equals 0, okay? F equals 0. When you come back, you have to come back original point, okay? Because of Stokes theorem. So consider the D here, the region D here, domain, and so this is path order, Okay. Sorry, this is in path order. Path order integral. Okay. So I think I should put exponential. That's more visible. I think 1 exponential of this one is indeed path order exponential. Can you see this one? So this path, it's path order. So if you look at the boundary, and do the integration, okay? So exponential of, so A is a one form, okay? Is a one form whose value is, okay, Lie algebra. And if you take exponential of, the physicists often write that from point P. So this will, the one, is it going to be one form? Yeah, it's one form. But it's now Lie group by exponential Lie algebra, you get the Lie group, okay? And now it's non-commutative, okay? So given the point, maybe I should, instead of U, I should U here. So point U1, point U2, you just receive the exponential of the AU1, and here you have exponential of AU2, okay? At each trajectory of this red circle, you have a Lie group, okay? But when you just integrate, do the integration, okay? Is essentially the this, if you, I mean, physicists always write like this way: exponential of sum of very small segment ui delta ui, okay, such that ui. Okay. That's usually what physicists have done. You do that. This integration, you just take the small segment u and sum them up. Okay? And this can be written as so this P is indeed P is a product. So the product of exponential, this sum becomes, I mean, e to the a plus b is e to the a and e to the b. Okay? It's a product, but you cannot, if A is the algebra, you cannot swap that. That you already know. This is not equal to e to the b, e to the a. So they're not, it's non-commutative. So you have to integrate in path ordered way. Path ordered way. Otherwise, it's not well defined. Do you understand? So if you take the AU I and then delta UI, okay, and sum over UI, multiplication is not it's not commutative. So you cannot. You have to specify the order, okay, how you multiply. So that's the path order multiplication. You have to do the path order multiplication. So at each point, when you go around, you have to always do that right multiplication, or left multiplication, or I mean, depending on which way you move around. So that's called path order. However, when f the connection is flat, by Stokes theorem, the exponential integral of this domain d of f over integral of f over d is equal to 1. Okay? It should be 1 because of its flat connection. Okay? So therefore, if this is contractible, you have to come back original point. You just add multiplication by 1. Identity element. Okay? On the other hand, if you take the other path, non-trivial path, okay, then you cannot apply Stokes theorem. There is no domain that bounds, that fill inside this orange line. Therefore, if you take orange line, this will go to somewhere else. Okay? Somewhere else. It can go to somewhere else. So this orange line is a, okay, maybe I should write that. Sorry, I think I should write, yeah, okay. So this orange line, not orange, yellow line. So if you follow this yellow circle, it can go to somewhere else on the fiber. And this difference is measured by this path order holonomy. It's called, this difference is called holonomy. What was that? Where should I write? This difference is called exponential p, exponential of gamma of a. So this difference is indeed, so this gamma is non-trivial cycle in a base manifold. So therefore, so what we have is, let me write down a bit more precisely. So what we have is the point P here, and you have a fiber. You have fiber G, and then, so we just assume some principal G bundle, whatever, to base manifold M, and then you have a non-trivial cycle, which is a generator of pi 1 of M, okay? Which is a generator of pi 1 M, and then so you have a flat connection. So you have a flat connection, F is equal to 0. And then connection will define horizontal direction. So that you can just move along the non-trivial cycle, and you get some holonomy group. Okay, element G. Okay. So maybe I can just use another color. You start with, then maybe it becomes like this. Okay. So this is gamma 1. We associate G1. Gamma 2, we associate G2. Okay? And G1, Gi is exponent path order exponential of A in gamma I. So this is called holonomy group. So namely, this G is the right action, so that this point U is moved to U times G1 here, and this one is U times G2. Okay? It's the right action on the principal G1. So therefore, we can have pi 1 to some G. So this is called holonomy homomorphism. So it's called holonomy homomorphism. So given a flat G bundle, one can construct holonomy homomorphism, which means that you assign non-trivial fundamental group, element of non-trivial group to this element. Okay? This guy. And then there is another subtlety. You have to be careful about the where you start. So where you start, and then do the same exercise, but now we use a different starting point. For instance, if you have a non-trivial element in here, okay, this gamma. For instance, you start with U here or B here. B here. Okay. U maybe my handwriting is horrible, so maybe I call P and Q. Let's call P and Q. You start with P and Q, and you have holonomy homomorphism. Let's say H. Okay. And then you do the same exercise, but you start point at a different point, Q. Okay? Q. Let's go, this one is, let's go L. The difference is L. Okay? And suppose P and is equal to Q times some element G. So there is a right action that connects to P, Q, and P. Okay. So then, what we have is H is equal to what we have is H is L is equal to G H G inverse. Okay. Okay. L is equal to GH inverse. Can you see that? I mean, my writing is a bit too small maybe here. So let me write them a bit bigger in upstairs. So what I did was polish. So what I did is that the fiber, let me write the fiber is very big. Very big, and the Q is here, and then P is here, okay, and then L is this holonomy group, P is the same holonomy group, but the starting point is different. This is H, and P and Q are related by G action, okay? So if you go to G action and take H and then come back to G inverse, then that is the same as this guy, this L movement. So G H and the G inverse is the same as just L. Okay, so that's what it means. Okay, so therefore, so depending on starting point, you have a conjugacy class. It's a difference is only like the gauge transformation coverage. So it's the conjugacy class of the gauge group G. So therefore, indeed, there is a one-to-one correspondence. F equal to 0. Flat G bundle. Well, flat G bundle. Flat G bundle. P over M. F equal to 0. This is called flat G bundle. Is one-to-one correspondence between holonomy homomorphism divided by conjugacy action G. So this divided by G means this conjugacy action. It depends on where you start. Okay. So this holonomy homomorphism divided by G. So there's a one-to-one correspondence between them. So therefore, so if you specify some holonomy homomorphism, so pi 1 to G mod G, one can construct flat connection indeed. So it's a bit different topic. I will give you some example, simple example later. So that is plays a very important role in transform theory. So usually people write, so it's a bit advanced topic. People write, so given the point, homomorphism pi 1 to of M to G divided by conjugacy class. Pick a point here. There is a one flat bundle, flat G bundle, with the corresponding flat G bundle. More precisely, this gadget, this object, parameterize a family of flat connections on tensor G bundle. And often people call this one is right this way, and which is called modular space. Flat connection. Modular space called flat connection. So pick a point here means that you just specify how it behaves. Pi 1 goes to M to G. So pick a point, given a point in modular space, flat, this holonomial is fixed as up to conjugacy action. So conjugacy means you just have an element just sandwiched by this element by group by adjoint action. So which means that you can define the some flat connection on a principal G bundle by constructing homomorphism, and I can give you some example. By the way, so I just give my lecture. note is updated last night. So if you should take a look at the most updated lecture note. And then I added some content last night. What did I say? Oh yeah. So let's consider the following thing. M is torus. M is torus. Some torus S1 cross D copy, which is usually D torus. Okay. What are the fundamental proof of this torus? What are the fundamental proof? So it becomes abelian. D copy of Z. Okay. And you just consider the map. So let's consider G is SU2. Okay. SU2 principal G bundle, principal of SU2 bundle, and you just consider the map between Z plus Z inside SU2. This homomorphism. So how do you construct this homomorphism? It's abelian, but this is non-abelian. The gauge cube is non-abelian. But let us say abelian. Abelian is commutative. Okay? True. But you have to construct a homomorphism. So the image has to be abelian. Okay? Since the pre-image abelian. Okay? So that this is abelian. So that the homomorphism, the image has to be abelian. Which means that it has to be diagonal. So each element, for instance, so I mean, it's just a bunch of circles. So the circle is S1, and the generator of Z is just S1 itself. Okay? So I call it a bunch of circles times S1 times so S1, let's go S11, S12, and so on. So this Si, so the generator, so let's go. This ice element, okay? So generator is just S1 itself is mapped some diagonal matrix xi, 1 over xi, 0, 0, okay? And the xi has to be the form e to the I theta I, okay? So it's SU2, inside SU2. So therefore, determinant has to be 1, and also if you take the complex conjugate and multiply, you should get 1. So therefore, it has to be U1 value, xi has to be. And the reason why it should be, the image is diagonal, is that everything has to be commutative. So as you know, xi and x1, 1 over x1, x2, 1 over x2 is equal to x2, 1 over x2, x1, 1 over x1. Okay? So that's true, right? But if you have off-diagonal element, this is no longer true. Therefore, everything has to be diagonalized. All the element has to go to diagonal element. Okay? So therefore, given a fix, if you fix the xi, one can construct this homomorphism. Okay? So therefore, the image, so image has to be also S1 cross S1 cross S1. Okay? They are parameterized by x1, x2, x2. Okay? xd. However, there's a conjugate sequence. What are the conjugate sequence? So this is conjugate sequence actually. So for instance, 1 x divided by x is conjugacy to the 1 over x. How do you see that? What does conjugacy mean? So if you take 0, 1, minus 1, 0, 0, 1, minus 1, 0, I think I should multiply an inverse so it should be minus. Okay? If you take this one, this is indeed equal to what? If you do the multiplication, then you get the x minus 1 over x, right? 0, 0. And if you multiply them together, you get this is equal to 1 over x, 0, 0. Okay? So the eigenvalue is swapped. Okay? X and 1 over x is swapped. So that's the same as z interaction. So the x and 1 over x is a conjugacy, it's the same conjugacy class. What was that? X. Oh, yeah. It's the same conjugacy class. So therefore, you have to do it simultaneously. Therefore, modular space of Flood connection, indeed, you have to divide by Z2. Z2 is just swapping the eigenvalue. So this is the modular space of Flood connection, TD SU2. This is the modular space. In particular, when you set D equal to 2, it's just 2 torus. It's a Riemann surface. It's a Riemann surface. So when D equal to 2, it's just 2 torus. You have a 2 torus. And the modular space of Flood connection of 2 torus of SU2 is indeed S1 cross S1 mod Z2. How does it look like? S1 cross S1 mod Z2 is indeed, so this is the original space, but modular space is also look like similar to T2 itself, but there is Z2 action. Okay? How do you do that? So fundamental domain of the universal covering of T2. Maybe I should write down this way. And you have, so one of them is spanned by eigenvalue x1 and x2. One is it? So this direction is x1 and this direction is x2. Okay? Okay. Sorry. Okay. So let's look at the origin here. So this Z2 action identify x and 1 over x. Okay. So there is a circle. This is S1, and the x is identified, 1 over x means what? So this is point x. Where is 1 over x sits in? At which point? Where is 1 over x? It's just here, okay? This is Sator and minus Sator, okay? Minus Sator. So therefore, everything opposite point is identified. This is Z2 action. Okay? Z2 action. In other words, the opposite point with respect to this origin is identified. Opposite point. Okay? The same here. The opposite point around this origin is identified. Okay? At the end of the day, you have, if you look at this region, okay, so this point is identified this point. So it's always opposite, right? And this point is the same as this point. Okay? So therefore, this point is identified this point. And then similarly, this point is identified, it's opposite to the origin, this point. But the fundamental domain, this point is identified with this point. Okay? Therefore, this torus is cut into the half, and this region is identified this region. Okay? Moreover, there's a fixed point. I think I should write bigger. Now I can write a bit bigger. So let's zoom into this part a bit. And you have to be careful. So this middle point is identified this middle point. Okay? They're opposite with respect to its origin. But it's the same point. Okay? It's the same point. So it's a fixed point. Namely, there's a fixed point by zeta action, this point and this point. Okay? So if you identify the zeta action, there's a fixed point. Okay? This fixed point appear and here and here and here and here. Okay? And indeed, this circle, half circle, is identified the opposite half circle. Therefore, this part is identified this part. Okay? Likewise, the other chunk, this part is identified this part. Okay? So you just do the folding. Okay? At the end of the day, the modular space looks like as follows. So at the end of the day, so this will become, and of course this point is identified, this point, this edge. So you just do the folding around this how to say, axis. You just folding. Yellow. Let's use yellow. And then you have identified also. So namely, I did yellow is identification is here, and the purple identification here, and this cut is this part, and this identification top and bottom identification is this one. Okay. At the end of the day, it looks like a pillowcase. Do you understand what I mean? So given a sheet, and you just identify the top and bottom and the edge, but inside this face is not identified the opposite face. Then at the end of the day, you get like a pillowcase. So the modular space of Flock function T2 mod Z2 is called pillowcase. So it's not manifold because there is a four singular point. So it's something singular happening in these 2 points, these 4 points. But apart from these 4 points, it's more like a manifold. It's apart from these points, if you remove these 4 points, it becomes manifold. Okay? So it's close to manifold. And indeed, if you move to M flat to sigma genus greater than 1, SU2, this one has the dimension, it becomes so-called symplectic. So I already told you symplectic. Moreover, it's Keller. Symplectic or Keller manifold of dimension what's the dimension? 6G minus 6. So it gives the structure of the simplex manifold. Even though it's a modular space, we just consider family of Lie connection. Family of Lie connection. Somehow you can give some manifold structure in the family of Lie connections. So let's take a rest for 10 minutes or something. Question?
Yes. I want to know why we should take half of the terms here. Because I think if we just folded the square, we can also that's it's more like
Because this part is already identified as red.
but this
Yeah. No, I mean, here, this point is identified as one. And this point is identified as one. So this region is identified this region. So by just swapping this one, just turning over. And this rectangle is identified as this rectangle. So you don't need to consider this one. Because this part is identified this one. And this part is identified this one. Both. Yeah, so it just acts simultaneously. So x1, one over x1, goes to one over x1, and x2, one over x2, goes simultaneously to one over x2. So you have to simultaneously.
This is just 1G, 1G in S2. Zero minus 1.
Yeah.
How do you know there is no other G that can transfer this diagonal matrix into the other diagonal matrix?
So I actually used to bring this one into this diagonal matrix. I use most of them. I fix most of the this conjugate conjugates plus fix some conjugates. So you can bring. So given that, so I just map everything. I just map everything to diagonal one. So x1, 1 over x1, total xt, 1 over xt. But it's totally okay. You just multiply everything g inverse g, any element.
Yeah.
Okay. Then
It's
no normal diagonal.
diagonal, but how do you know there is no other element except 0 minus 1, 1, 2?
Because you can just group it.
Okay.
Can you find out something else? You should try. Oh, big deal.
Oh,
Can you find something else? If you can find it, that would be amazing. I don't think you can do that. It's actually easy to show. It's just 2 by 2 matrix, so you set G is equal to alpha beta minus beta star alpha star, where alpha square and plus beta square is equal to 0, equal to 1. And just multiply x 1 over x, and then alpha, and it's just do the form, right? The beta star and alpha. And then just solve the equation. This is 0, 0, some other element, 1 over 1. And if you solve the full equation and then for variables, so you can solve it. Now at the end of the day, what you get, essentially, you get that beta is equal to either 1 or alpha is equal to 1. I think that's what everything matters. Yeah, I think that's what you do. Okay, so shall we resume? Okay, so I just give you one example for Jacobian, but then let's omit the Jacobian. Jacobian is when g equal to u1, and then g equal to u1, and then M is Riemann surface. Maybe you can, I don't know, you can brief it if you want. Okay, then let's go to transience, as I promised. So, transience theory. So M is oriented towards my semi-manifold. Okay, and then principal G bundle is always split. In this case, and it's always trivial. It becomes always trivial. G bundle. So action is given by so this is the transience action. Or if you write indices, this is trace of mu version mu arrow plus 2/3 mu arrow times epsilon mu euro. I think I have to be careful of sign as well. Yeah, I think it's okay. 4 bonds. Okay. So this is the action. You have the main difference between Yang Mills. So Yang Mills is the so this is Yang Mills action for general manifold M. So in both metric G, Yang Mills. Okay. We always Yang Mills action involves metric G. So in other words, this can be written as oh sorry, so I should use trace. Sorry, trace of F U F or sigma. This can be written as average topology. Okay, so that's what you saw in the homework. You always involve this hot star. And a hot star depends on the metric. Okay? So therefore, the action on MLs really depends on the metric you consider. So you have to consider always Riemannian manifold you start with. Okay. On the other hand, for transaminds, you don't need the metric. You just start with 3 manifold, no metric. Okay? No metric is involved. That's the main difference. Now what is the equation motion for the transaminds? The reason why I talk about Flock collection is that because once you take variation with respect to A, it's super easy to see. So this transaminds number A is equal to F is equal to 0, some number. Oh, sorry. And also I should mention K is called level. It's called K is called level. And then it's kind of inverse coupling constant. Inverse coupling constant. So you can easily see for instance, if you take variation with respect to A, what's left is dA, right? And the delta A, and if you have to pick 1 out of 3, 3 cancel with this 3. Okay, so therefore, and you have to pick one of them, so you get 2. So essentially, you get 2 times dA plus A squared. That's what you get after variation with respect to delta A. Okay. So you have this is a Flock function. So the equation motion is Flock function of transaminds is the Flock function. So I think I made a mistake. Okay, let's look at the Boolean transaminds. So let's consider G is U1 case, then F is equal to just the A, sorry, and transaminds action is scale over phi, and then ADA. That's it. There is no Q term because of it's immediate. So then, so you can consider, so for the path integral, the following thing. Okay, that was okay. Okay. And then, so this one, so this is path integral, so this is spatial connection. So this one is first considered by 1978 Alois Schwartz. So, and he got the so-called Latimer's torsion. It's called torsion. Latimer's torsion. I mean, this is a bit too difficult for you guys. I need a technique like Latimer's torsion. This one is the first instance called now it's called TTFT. So this one, you have to do so-called use one loop determinant. Unfortunately, this is not a lecture of QFT. I'm not going to explain this one, but this is first instance, first example to get first example of TQFT that appeared in the literature. 1978, Albert Schwartz. Schwartz is a Russian mathematical physicist. Yeah, he's very unique character. He's really original. I mean, he's very original person. I mean, all of his books are very original. But instead, I just consider the following quantities. So the dimensions, so there's the holonomy homomorphism. So in this case, G is U1, so there is no need to consider, so it's abelian, so it's commutative. So there's no need to consider the path order. So this one holonomy group is often called holonomy is called Wilson loop in literature, in physics literature. Consider the following in quantum field theory. So now this field A is some can be the quantum observable. So you can just put consider like expectation value of this Wilson loop. So now we consider manifold M, C manifold M. There's a topology inside. So now gamma is something, whatever. Gamma can be like this way, or maybe gamma can be something like this one. So S1 embedding, so the S1 is embedded inside NC. So let's see. You can consider the expectation value in the path integral. You just consider all the computation of the here, and but you insert so-called Wilson loop also. So this is the vacuum expectation value. In particular, what the interesting thing happens when you have the link. So link. K1 and K2. So this link can be written down like this way. So this can be written like this. So it's now abelian, so you don't need to consider the order of a multiplication, so it's commutative. And now, So this can be written as follows. Like this. The Billion-Chen-Simons. So Billion-Chen-Simons expectation value of x, and so it's a two-point function that can be easily computed, which takes the following value. Its propagator. So in 3D Chen-Simons and 3, U1 Chen-Simons 3, and 3 propagator. Can be computed easily. Like this. And then physicists often write this one is like this way in quantum physics. It's a bit ad hoc, and then let's plug up into it again. It's final propagator. You will learn once you take QFT, but just use this relation, but you get this exponential. 4 pi I divided by k. Oh, sorry, x1, x2, x1 minus x2, and the row divided by x1 minus x2. So this is the answer obtained from the from just plug this one into here. I think 2 pi. I think I missed 2 pi I somewhere. I think I should put 2 pi I somewhere. 2 pi somewhere. Oh, no, it's okay. It's okay. Sorry. This is not fine. And then this one you already learn in this integral you already learned in the long time ago, but around the Hop theorem. Hop theorem, the last, so the Hop theorem tells us that the mapping degree S1 plus S1 of to S2. Okay. Mapping degree F. So degree of F can be written is 1/4 pi is the this K1. Dx mu, dx2 mu, x1 mu rho. So x1 minus x2 rho divided by exactly the same integral. And this one can be understood as the so you have a K1 and a K2, and then here you have a X1, its parameter of X1 and X2, and then mapping to S2, you just take the relative vector between them. So relative vector between them, x1 to x2, and take norm. Okay, take norm, divided by norm, and just integrate out. Okay, and that will give you mapping f. So that will give you the f. Define the map f to the torus to S2, and its mapping degree is just a pullback of the volume from S2. That is given here, and that is linking number. So that's what we have learned in a long time ago, and this is what really happened. So this is indeed equal to exponential 4 by I divided by k, linking number k1 and k2. So abelian elements, once you divide the link expectation value, you get the linking number. And as I mentioned, this linking number can be understood as 1/2 sum of positive and negative crossing, right? Positive crossing, I is crossing. So in other words, if you have the two link like this way, and you just assign this one is positive crossing and the negative crossing is the opposite. And if you sum them up, you get the linking number. So in this example, you get the linking number -1. Okay. So this example, you get the linking number -1. So somehow, and this is link invariant. So link invariant, even if you just deform this link in arbitrary way, it doesn't matter. Okay? So which means that so this one can be just deformed like this one maybe. Right? You can deform like this way. Okay. And even if you create two additional how to say, linking, it's not linking, but it's a crossing. It's crossing. But if you look at the definition plus or minus, this becomes whatever. Maybe this becomes, this is a minus sign, this is positive. So they cancel. Therefore, it's a linking invariant. It's a topological invariant. Okay, so this is a work by particle. This is particle. Then, so what about U1 is indeed, I can continue this once I talk about transcendence, I can continue indefinitely. But I don't know how much I can talk about it. So G is non-abelian case, G is non-abelian B group, general Lie group, non-abelian. So the Wilson loop over there is again, so you need to pass all the exponential of delta A gap. You have to. And also, it depends on how you start, which point you start in principal G bundle. Then, again, so if you change the starting point, you have the conjugacy twice, like this. Okay. So to make it well defined, what you can do is take the trace. If you take trace of this guy, then this, in a non-abelian case, this is called Wilson loop. In an abelian case, you have to use path order, so that the inside the trace G inverse and G cancel inside the trace. Okay, inside a trace, this is equal to, it's well defined, or it's independent of where we start. How much do you want me to talk about this transcendent? So then you get the same exercise. Now, so we have so what we didn't tell us that this guy is the vacuum extraction body. Mindful. Oh, sorry. So this is not M, sorry. Space of connection divided by gauge group. So you just consider expectation values of Wilson loop, and this will give you so-called important invariance of knot. Depends on let's go instead of gamma, let's go K. Maybe K is better. Now I just avoid it because capital K is just a bit hard to distinguish the small K, but then it's okay. I think capital K. Okay, and this depends on the supporting variable. So what Witten tells us that this, even though it's the infinite dimensional integral, like this U1 case, if you use this propagator, so this propagator, so we reduce this infinite dimensional integral to some finite answer, some just linking number. It's very simple. And the non-linear case, so when especially G equals U2. Q, I introduce Q is exponential 2 by I divided by K plus 2. This K is a level. And in particular, in non-linear case, K level has to be integer. In order for path integral to be well defined, integral to be well defined. So K is called Chern-Simons level, often it's called Chern-Simons level. Its K is integer. And it's really two come from these two. And then this Wilson loop is the same as what you can compute the following generation. So this is the this expectation value can be computed in M is side. SU2 and M is equal to S. let's do the some computation. So even though we cannot, this is fine. There's an infinite dimensional part integral. Part integral. So nobody knows how to perform, but one can compute the Wilson Lipton expression value in its very easy way, easy manner. So let me do the following exercise. So let's do the following exercise. Let's compute the S3, the S3. And then you have so-called triple. Yeah. So that's this is called triple. Then appear in the I'll be part of lecture and then do the following exercise. So Jones of this one and apply scaling relation. What was the culture? And then just give some orientation. And apply into here. Okay. So then what you have is that so you have here, if locally, this yellow part locally look like this one, okay? Locally, yellow part look like this one. And so therefore, this can be understood as Q2 force. I think, am I doing correctly? I think minus 4, to the minus 4, J. Am I doing correctly? If I make a mistake, I don't get the right answer. That's why this is okay, right? Yeah, I think it should be okay. I think my mode is wrong. So. Okay. Inside. Okay, so you just, since it's locally this one, this yellow part, locally look this one, just replace this one to this plus this with up to Q factor. Okay? So then what you get is this one and then this one. So it becomes a positive crossing to negative crossing, and another is resolution. Okay? And you have to multiply Q to the minus 1, Q to the minus 2, then you get the Q to the minus 4, and you just bring this one to the right hand side, you have a plus sign, minus 2, you have at the, oh my goodness, I think this should be plus 1 and minus 1. Oh, sorry. Okay. I think now it looks okay. And here you have another crossing here, and you apply the same thing. Okay. It's very easy. So this one also looks like very similar to this guy. So let's do another exercise. And this one is equal to q to the minus 4. And j is, this is indeed is the same as unknown. So it's called just circle. It's called unknown. It's called unknown. And then minus q to the minus third plus q to the minus 1. And apply the same thing into here. And what you get is times so once you apply the extendation, what you get is indeed q to the minus 4, okay, and then plus q to the minus 1, q to the minus third, and then j, and then single one. Okay. So if one is resolved like this way, okay, one is becomes, so that corresponds to this one, okay. So then this one is corresponds to this guy. On the other hand, if you resolve like this way, okay, then it becomes like this way, okay, and then you have to multiply a product factor. So now let's compute the. And in physics, we often assign, so this R naught is equal to, so Barking extension value is indeed, this R naught is called quantum number 2. What's quantum number 2? Q squared minus q to the minus 2, q to the minus 1. This is called quantum number. Do you know why it's called quantum number? If you do the computation, you have q plus q inverse. Okay? When you set q equal to 1, it becomes 2. Now generally, quantum number n is defined as follows. And plug that one into here, what you get is q to the minus 4, q plus q inverse. Okay? And now you have q minus 1 minus q minus 3, q to the minus 4, and the q plus q inverse square, and then q plus q inverse q minus 1 minus 5. Okay. That's what you get. It's just a run-out polynomial. Do you agree? You should be okay if I don't make any calculation mistake. And then you can just have a common factor. And then let's do the computation. I don't like, I never do the computation. Q minus 4. Plus, oh my goodness. It's a difficult. Difficult on the imagine. Okay, let's do it here. And then this is equal to, let's see. This is equal to q plus q inverse q to the minus 4 plus q inverse plus minus q to the minus third, q to the minus fourth, q plus q inverse, plus q inverse minus q to the minus 3. Okay? And this one is the same. Q to the minus fourth. And then 1 minus q to the minus 2 plus q to the minus 2 minus q to the minus 4. And then I have to shift like 4. Just correct me if I'm wrong, if I make a mistake. Okay? And then what you have, I'm pretty sure now I made a mistake. Oh gosh. Oh, maybe there's a problem. Okay, so this is the computation you get. And then this guy cancel with this guy. Okay? And what else will cancel? This guy will cancel with this guy. And you get this one, this one, this one. Okay? Oh, okay. I got a result. And then q3 minus 2 plus q3 minus 6 minus q3 minus 8. Good. So this is called John's polynomial of circle. So good exercise to do. So this diagram, so we started with this diagram, and indeed this is the same as this one. And it's a good exercise to do. This diagram is the same as this diagram. Can you see that? Bring this one into here, you become like this one. Bring this one into here. And the orientation, I don't know which one, maybe I will imagine this one. Do the same exercise, whether you obtain the same answer. Do the same exercise, you should obtain this one. You should obtain this one. So, the upshot is that even though so the upshot is that even though we consider very complicated non-trivial path integral, at the end of the day it becomes a Laurent polynomial. So the expectation, this is the expectation value of triple. A is triple. A if G is equal to SU2, and then F is equal to S. And it's invariant under the it's invariant on isotopy, so which means that even if you change this one into this one and apply the scale relation, so you get the same answer. So in more precisely, it's this, and this is called scale relation. Even though we start with very complex path integral, at the end of the day, all the computation reduces to this simple scale relation. Everybody can do it. Even I can do it, even though I didn't have the lecture. The reason why is the following. The reason why it becomes so simplified is the following. So in the exercise you will see So this is not written in my lecture note, but let's see. Where should I start with? Yeah. So then, so if you consider that M3 has a boundary. So then, it's called bulk. So this one is explicitly often called bulk and a boundary. So the bulk on M3, you have Chern-Simons actions. It's Chern-Simons. I already write down. So I can write down trace ADA plus 2/3 A cube. But on sigma, you have so-called Witten model, which takes the following form. The upright body, I really forgot. The trace of dg, which star dg of sigma. And I think it's h pi and plus k over. Sorry, I just need to fix the sign. This is one of the homework in the today. Next week. What was the homework? Is the I need to be fixed the coefficient. Yeah, k over k over 4 pi. Okay, k over 4 pi. And then I think I should write down like this: a g inverse dg, which g inverse so this is generic term, but you have another term which is 12, and then M3 and trace of g inverse dg, which g inverse dg, and which g inverse dg. So this is called what's the Witten model, where g is the indeed the M3 the group manifold gamma. So, in particular, I can just move to here. In particular, one can associate so one can associate the sorry, that's too many. Yeah. So one can associate the partition function of this M3 if the boundary of M3 is indeed the Fourier space associated sigma. It's called Fourier space, the vector space. Finite dimensional vector space. That is associated with the Witten model. In particular, so So this is often called homomorphism, space of homomorphism. So the nice thing is that even though it's a finite dimensional path integral, it becomes element of finite dimensional vector space. And then, for instance, this scaling relation can be obtained by the following way. I didn't write the lecture. I didn't have time to write down everything. Where did I put? Sorry, where did I put that? This is the scaling part. Oh yeah. So the scaling relation can be understood as follows. So in particular, this scaling relation can be obtained with just ball, half ball, and the Wilson loop attached. It's a fundamental. So it's attached, and this is called L plus, and another is the other element, other. And then other configuration is and then it turns out that if you consider a dimension of Hilbert space equal to 2 associated to this S2, so at the boundary, so this is 3 ball, and at the boundary you have a sphere with 4 punctures. Sphere with 4 punctures, 3-point puncture. So there's a 4-point puncture. So they are created by Wilson loop. Okay. And then and this 4-point Hilbert space is in 2-dimensional. That's the reason why is that the spin 1/2 times spin 1/2 times spin 1/2 is equal to 3 plus 1, right? 3 plus 1. Decomposition is, well, precisely, you have in young table language, you may have heard of it. It becomes this decomposition. So these two are the states. It becomes states in Hilbert space of S2. So therefore, even though there is a two-dimensional, you have a three vector coming from Chen-San. Okay? Coming from Chen-San. Therefore, there must be a linear relation, L minus and L naught. So linear relation between them, and I'm also writing all the time. So there's a linear relation. So alpha L plus beta L minus plus gamma L naught has to be 0. So because since it's two-dimensional, but you have a 3 states, there must be a linear relation. And that can be easily fixed by capping off by unfortunately I don't have the so for instance you can just cap off like this way. You can cap off like this way. I think that there is somewhere. I think if you cap off the inside, if you do like this way, what's going to happen? No, what I'm doing is, sorry. No, that's all it's going to happen. So, sorry. Okay. yeah, I mean, you can cap off the yeah, essentially what you get is this relation. So from here, alpha plus gamma plus beta minus equal to 0. And also you can do some braided group relation. So I just give you the last comment. So if you use the braiding, so if you use the braiding in between them, you get another relation. So at the end of the day, so what you get is minus q to the squared plus q to the minus 1/2 or not plus q to the q squared is equal to L minus equal to T. Maybe next time I will explain a bit more detail how to obtain alpha, beta, gamma. But from here, we're working. This is the same as scalar relation. So the same as scalar relation. So the upshot is that the important thing is that in Chern-Simon's previous case is finite dimensional vector space. So that if you use the braiding operation, one can obtain it easily with the scalar relation. So that's a typical feature of T2FT, So that one can evaluate without performing path integral. Just using relation to boundary, you can obtain the Wilson expression. Okay, let's stop here. Sorry for running over time.
So do you understand what you said is wrong?